Have you ever wondered if there is a way to travel to another universe? Well, wormholes might just be the answer. These hypothetical tunnels in space-time could serve as shortcuts through the cosmos, allowing travel to distant realms in the blink of an eye. So how do wormholes work? While the concept of wormholes may sound like science fiction, the mathematics behind them are grounded in the principles of general relativity. Einstein's equations allow for the existence of these cosmic shortcuts, leading scientists to explore the possibilities they offer. According to theoretical physics, wormholes are thought to be connections between 2 points in space-time, creating a shortcut that bypasses the traditional route. This means that you could potentially travel to a different galaxy, or even a different time, by simply entering one end of the wormhole. But creating and stabilizing a wormhole is no easy feat. The immense energy and exotic matter required to keep the tunnel open pose significant challenges. Scientists are still working to unlock the secrets of wormholes and make inter-universal travel a reality. Wormholes are theoretical entities that exist within the framework of Einstein's theory of general relativity, a theory that has been proven correct repeatedly. They are bridges or tunnels that could, theoretically, link different points in space and time. Some theories even suggest they could connect to entirely different universes. Now, you might be wondering, if wormholes are a part of established scientific theory, why haven't we seen or used them yet? Well, it's not that simple. While the mathematics of general relativity allows for their existence, we have yet to find any empirical evidence of wormholes. They remain, for now, purely theoretical. But let's not let that put a damper on our excitement. Theoretical or not, the possibility of wormholes opens fascinating possibilities. If they do exist, they could provide us with shortcuts across cosmic distances, making interstellar or even inter-universal travel a reality. Imagine for a moment stepping into a wormhole and emerging in an entirely different universe, with its own unique laws of physics and exotic forms of matter. In the realm of the unknown, the only limit is our imagination. So let's keep our minds open to the remarkable potential of wormholes. It's a thrilling journey into the depths of the cosmos, and we're just getting started. Let's dive into the intriguing science of wormholes, shall we? So, what exactly is a wormhole? This question has intrigued scientists and sci-fi enthusiasts alike for years. Let's break it down and make it as simple as possible. Imagine a piece of paper. Now, if you wanted to get from one side to the other, you'd usually just travel across the surface, right? That's the standard way. But what if we could do something different? What if we could fold that paper, bringing 2 distant points close together and then somehow drill a hole straight through? That is a wormhole. In scientific terms, a wormhole is a theoretical passage through space-time, created by warping the fabric of the universe itself. They're like tunnels with 2 ends, each at separate points in space and time. One could be in your bedroom and the other might open on the dark side of the moon, or even in another galaxy. When we talk about space, we often think about it in 3 dimensions: up and down, left and right, forward and backward. But Einstein told us that time is a 4th dimension, inseparable from space, creating what we call the fabric of space-time. Now imagine if we could fold this fabric, not unlike our piece of paper, and create a shortcut. That's the concept behind a wormhole. Wormholes are fascinating because they're not just about space, they're about time too. They could potentially connect not just 2 different locations in the universe, but also 2 different moments in time. That's right, we're talking about real-life time travel here. But how do we get these magical tunnels? The idea comes from Einstein's theory of general relativity, which describes how massive objects like stars and planets curve the fabric of space-time around them. This curvature creates what we feel as gravity. Now, if the space-time fabric can be curved, then perhaps it can be twisted and folded to create wormholes. However, it's essential to remember that wormholes are purely theoretical at this point. While the math of Einstein's theory allows for them, we've yet to find any concrete evidence that they exist. But that doesn't stop us from exploring the possibilities and implications. Imagine if we could use such a shortcut to traverse the immense distances of the universe. The farthest reaches of space might be just a step away. It sounds like the stuff of science fiction, but who knows? Today's science fiction often becomes tomorrow's science fact. So here's to the dreamers, the thinkers, and the explorers, pushing the boundaries of our understanding. After all, the universe is a big place and there's still so much to discover. Imagine if we could use such a shortcut to traverse the immense distances of the universe. Wormholes aren't just science fiction, they're grounded in real science. Now let's delve into the theoretical foundation of wormholes, also known as Einstein-Rosen bridges. The seed for the idea of wormholes was sown by none other than Albert Einstein and his colleague Nathan Rosen, and it's deeply rooted in Einstein's groundbreaking theory of general relativity. This theory, presented in the early 20th century, fundamentally changed our understanding of gravity. It suggested that gravity wasn't simply a force pulling objects together, but a result of how massive objects warp the fabric of space-time around them. Imagine a rubber sheet stretched taut. If you place a heavy ball on it, the sheet will curve downwards under its weight. Now if you roll a smaller ball towards the larger one, it will roll along the curve toward the bigger ball. That's a simple way to visualize how gravity works according to general relativity, but what happens if the mass is so immense that it doesn't just curve space-time but punctures it? Well, that's where the concept of wormholes comes into play. Einstein and Rosen took their theoretical exploration a step further and proposed the existence of bridges in the fabric of space-time. These bridges, or wormholes, would be shortcuts connecting two distant points in the universe. Now, these Einstein-Rosen bridges aren't your ordinary bridges. They're more like tunnels, where you'd enter from one side and exit from the other, potentially millions of light years away. Imagine stepping into a portal in New York and stepping out in a galaxy far, far away. That's the promise of wormholes. Of course, it's important to remember that all of this is theoretical. While general relativity allows for the existence of wormholes, we've yet to find any concrete evidence of them. But the beauty of science lies in its relentless pursuit of the unknown, its unyielding quest to turn theory into reality. So these bridges in space-time, these wormholes, remain one of the most fascinating subjects in theoretical physics. They challenge our understanding of the universe and its laws, and they open a world of possibilities that stretch the limits of our imagination. But we're getting ahead of ourselves. Before we start packing our bags for an intergalactic trip, there are a few challenges to overcome. Theoretical physics is one thing, but practical application is another. Traversing a wormhole might not be as easy as stepping through a door. Indeed, the concept of wormhole travel, while fascinating, is fraught with numerous scientific challenges. Today, we'll dive into the deep end of these challenges, which include wormhole instability, the need for exotic matter, and the potential dangers of traversing a wormhole. Let's begin with the issue of instability. Theoretical physics suggests that wormholes, if they exist, are incredibly unstable. This instability arises from the intense gravitational forces at play. Imagine trying to balance on the tip of a needle while the ground beneath you is shaking. That's akin to the instability of a wormhole. The slightest disturbance, even a single subatomic particle, could cause the wormhole to collapse. And if you're unlucky enough to be inside at that moment, well, it's not a pleasant thought. This leads us to the second challenge, the need for exotic matter. Now, when we say exotic, we don't mean something you'd find in a trendy cocktail bar. In the realm of physics, exotic refers to a type of matter that's not just rare, but might not even exist. This exotic matter would need to have negative energy density, a concept that's as strange as it sounds. It's matter that's less than nothing. This is the kind of stuff that could theoretically keep a wormhole open, counteracting its natural tendency to collapse under its own gravity. However, we've yet to find any proof that such matter exists. Another hurdle in our quest to conquer wormholes is the potential danger of traversing them. Even if we manage to stabilize a wormhole and find the exotic matter to keep it open, there's still the issue of what happens when we pass through. According to some theories, the journey could be extremely hazardous. The intense gravitational forces could cause spaghettification, a process where an object is stretched into long, thin shapes like strands of spaghetti due to extreme differences in gravitational pull. As you can imagine, this wouldn't be a particularly pleasant experience for a space traveler. Beyond spaghettification, there's also the risk of incalculable radiation. As we've learned from studying black holes, areas of intense gravity can also generate extreme amounts of radiation. If a wormhole is similar, then anyone or anything passing through could be subjected to deadly levels of radiation. Lastly, there's the challenge of time. Theoretical models of wormholes suggest that they could connect not different points in space, but different points in time. If this is true, then a journey through a wormhole could potentially lead to time travel, with all its associated paradoxes and complexities. For example, what happens if you travel back in time and prevent your own birth? This is known as the grandfather paradox, and it's just one of the many mind-bending dilemmas that time travel presents. As you can see, the challenges of wormhole travel are vast and varied, stretching from the realms of theoretical physics to the limits of our understanding of the universe. We're still in the initial stages of understanding these cosmic shortcuts, and it's likely that many more challenges will arise as we delve deeper into the science of wormholes. However, it's important to remember that these challenges aren't roadblocks, but stepping stones. Each one represents a question to be answered, a puzzle to be solved. And with each solution, we edge closer to unraveling the mysteries of the universe and one day, mastering the art of wormhole travel. The journey through a wormhole might be more perilous than we can imagine, but that peril also holds the promise of discovery, of new knowledge, and of a future where the farthest reaches of the universe might be just a wormhole away. Despite the challenges, the potential of wormhole travel is staggering. Now let's take a moment to envision a universe where the challenges of wormhole travel have been overcome. What does that look like? Well, the implications are as vast as the cosmos itself. Firstly, we have interstellar travel. The vast distances between stars are one of the greatest barriers to our exploration of the universe. Even at the speed of light, it would take us over 4 years to reach the nearest star, Proxima Centauri. But with wormhole travel, these cosmic distances could become mere stepping stones. We could move from one star system to another in the blink of an eye, exploring distant worlds and civilizations that we can only dream about today. Beyond just interstellar travel, wormholes could also give us access to other galaxies. Our Milky Way galaxy is just one of an estimated 2 trillion galaxies in the observable universe. With wormholes, we could potentially explore these distant galaxies, broadening our understanding of the universe in ways we can't even fathom. And then there's the potential for time travel. Yes, you heard that right. According to the theory of general relativity, we know that gravity can bend time. So a sufficiently advanced civilization might be able to use wormholes to travel not just through space but also through time. Imagine being able to witness the birth of the universe or see what the future holds. But the most significant prospect of all is the potential access to other universes. You see, some physicists believe that our universe may not be the only one. There could be countless other universes out there, each with its own unique laws of physics. Wormholes could potentially be our gateway to these other universes, opening up possibilities that are truly beyond our wildest dreams. Of course, all these possibilities hinge on one big if. If we can overcome the immense challenges that stand in the way of wormhole travel. And that's a big if. But isn't that what science is all about? Pushing the boundaries of what is known, daring to dream big, and striving to turn those dreams into reality. So as we continue our journey into the unknown, let's remember that the potential of wormhole travel isn't just about science or technology. It's about our human spirit, our desire to explore, to learn, to grow, and who knows. With our unyielding curiosity and our relentless pursuit of knowledge, we might just be on the cusp of the greatest discovery in human history. So where are these wormholes? Can we find them? The quest for real wormholes is as thrilling as it is elusive. Theories abound, but we haven't found any definitive proof. However, that doesn't mean we aren't trying. Both astrophysicists and astronomers are persistently peering into the depths of space, hoping to catch sight of these mysterious structures. Let's talk about the current scientific endeavors to detect wormholes. The task is not as simple as looking through a telescope. You see, if wormholes exist, they are likely to be incredibly tiny, microscopic even. Quantum mechanics suggests they could be as small as a billion trillion trillionth of a centimeter. That's a decimal point followed by 33 zeros and a 1. To make things even more challenging, these tiny wormholes might exist for only a fraction of a second before collapsing. But even if we can't see them directly, there might be ways to detect their presence. One proposed method involves studying the behavior of stars and galaxies. If a wormhole were present, it could potentially distort the light from distant objects in a specific, recognizable way. This is like how we detect black holes, which are also invisible. Another method involves looking for unexplained energy bursts. Some theories suggest that when a wormhole opens, it could release a burst of particles and radiation. If we observe a sudden, unexplained burst of energy, it might be a sign of a wormhole. Now let's take a closer look at the astronomical observations being carried out in this field. Astronomers are constantly scanning the night sky, looking for anomalies that might hint at the existence of wormholes. They use a variety of tools, from radio telescopes to X-ray observatories, in their quest to find these cosmic shortcuts. And then, there are the studies. Teams of scientists around the world are diligently working to solve the mysteries of wormholes. They conduct experiments, create mathematical models, and run complex simulations, all to understand more about these fascinating structures. One of the most interesting studies has come from the research team at the University of Buffalo. They've proposed a way to detect wormholes by looking for slight changes in the brightness of stars. If a star's light path crosses a wormhole, the wormhole's gravity could cause the star to appear brighter. This could provide a way to detect wormholes even if they are too small to see directly. Of course, all this research is still in its preliminary stages. We are just beginning to scratch the surface of what might be possible. But the search for wormholes is not just about finding a shortcut through space, it's about expanding our understanding of the universe and our place in it. It's about pushing the boundaries of what we know and venturing into the unknown. And so the search continues. Every day, scientists around the world are looking, studying, and hypothesizing, trying to bring the science of wormholes out of the realm of theory and into the realm of reality. Who knows? Maybe one day, we will stumble upon a wormhole. The science of wormholes is still in its infancy. Just as a newborn child is full of limitless potential, so too is our understanding of these cosmic shortcuts. The future of wormhole research is an exciting prospect, laden with possibilities that could fundamentally shift our understanding of the universe as we know it. Let's begin with a simple question. What if we could harness the power of wormholes? This isn't just a question for science fiction authors and their imaginative tales. It's a question that scientists are actively exploring. The potential advancements in technology that could come from wormhole research are staggering. Consider space travel, for instance. The vastness of space is a significant barrier to our exploration of the cosmos. As we discussed earlier, even at the speed of light, it would take us 4 years to reach Proxima Centauri. But if we could create or find a wormhole that links us to that star system, the journey could be instantaneous. This would revolutionize space travel and potentially open the universe for exploration in ways we can hardly imagine. Moreover, the study of wormholes might also lead to advancements in communication technology. If we could send information through a wormhole, we could potentially communicate instantaneously with distant parts of the universe. This could revolutionize not just our understanding of the cosmos, but also how we interact with it. But it's not just about technology. The science of wormholes could also lead to profound shifts in our understanding of the universe itself. For instance, it could help us answer some of the most fundamental questions in physics. One of these questions is the nature of gravity. Einstein's theory of general relativity tells us that gravity is caused by the curvature of space-time around massive objects. But there are still many things about gravity that we don't fully understand. If wormholes exist, and if we can study them, they might provide us with a unique laboratory for probing the nature of gravity in ways we can't do with any other phenomenon. Another fundamental question is the nature of time. If wormholes exist, they might allow for time travel, at least in theory. This opens a whole Pandora's box of paradoxes and puzzles, but it also offers a tantalizing possibility for understanding the nature of time itself. If we can understand how time works in a wormhole, we might gain insights into the nature of time in our universe. Of course, these are all big ifs. The science of wormholes is still in its infancy, and there are many challenges to overcome. But that's the beauty of science. It's a journey into the unknown, a quest for understanding that is driven by curiosity and wonder. And who knows? One day we'll find a wormhole or create one. We'll send a probe through it or even a human. We'll see what's on the other side and we'll learn something new about the universe. Or we'll discover that wormholes are just a figment of our mathematical imagination, an artifact of our theories that doesn't exist in the real world. Either way, the future of wormhole research is bright, full of potential and promise. It's a journey that we're just beginning, but it's a journey that could take us to the stars and beyond, to the very edge of our understanding. The science of wormholes might just be the key to unlocking the secrets of the universe. So join us as we continue this exciting journey into the unknown, because who knows what wonders we might discover along the way. We've journeyed through the fascinating world of wormholes. We started off by probing the unknown, diving into the mystery that surrounds these cosmic shortcuts. We delved deep into the cosmos, trying to grasp the concept of wormholes, these tunnels in the fabric of space-time that could potentially link two disparate points in the universe. We learned that wormholes aren't just figments of imaginative science fiction writers, but they are a part of the solutions to Einstein's field equations of general relativity. These equations describe how mass and energy in the universe can warp the fabric of space and time. A pair of physicists, Albert Einstein and Nathan Rosen, gave us the concept of the Einstein-Rosen bridge, a theoretical model of a wormhole. But as intriguing as these cosmic gateways are, we also learned that they present numerous challenges. Wormholes, as we understand them now, are highly unstable. They would require some form of exotic matter with negative energy density to keep them open. This is a type of matter that we have yet to discover and understand. The dynamics of traveling through a wormhole could be incredibly dangerous as well. Rapid changes in gravity could stretch and squeeze anything passing through to the point of destruction. Yet, despite these challenges, we explored the potential of wormhole travel. If we could stabilize a wormhole, it could serve as a bridge to another universe, or a shortcut to a distant part of our own universe. Imagine being able to journey to the farthest reaches of the cosmos in the blink of an eye. We also discussed the ongoing search for real wormholes. Scientists are constantly on the lookout for these cosmic shortcuts. We don't have concrete evidence of their existence yet, but indirect signs could potentially point us in the right direction. For instance, if a wormhole were linking two areas of space, it could leave a detectable imprint on the light that passes through it. Scientists are also using advanced technology like the Event Horizon Telescope to probe the edges of black holes where wormholes might exist. And finally, we look towards the future of wormhole research. It's a field full of possibilities and unanswered questions. Will we ever find a real wormhole? Can we learn to create and stabilize them? And if we do, what will that mean for space travel, for our understanding of the universe and even our own place within it? The beauty of science lies in its endless quest for answers, and wormholes, these potential gateways to other universes, are one of the most intriguing mysteries we are trying to unravel. The research is ongoing. The journey is far from over, and each new discovery could potentially revolutionize our understanding of the universe. As we wrap up our journey through the fascinating world of wormholes, let's remember that each step we take towards understanding these cosmic gateways brings us one step closer to understanding the intricate tapestry of the universe itself. The possibilities are limitless, and the potential discoveries could change our perception of reality. Until we find a wormhole, we can only speculate. But isn't that the beauty of science? It fuels our curiosity, drives our exploration, and constantly pushes the boundaries of our knowledge. So let's keep probing, keep questioning, and keep exploring the cosmos. Who knows what we might discover next?